Okay, so we are now in lesson 7.3, okay? We are in lesson 7.3, so we are now looking at linear inequalities, okay? So we've been dealing with linear equations, and now we are dealing with linear inequalities. So we're going to talk about how do we write and graph linear inequalities, as well as what is a boundary line. So that's going to be something we need to know for this lesson for understanding linear inequalities. I notice this camera is probably not perfect for you, so I'm going to try to fix it a little bit. Okay. All right. There, that should be better. Great. Cool. So we are dealing with linear inequalities. We're going to talk about how do we write and graph linear inequalities, as well as what is a boundary line. Recall, a graph is used to display the solution set of an equation. Okay? A graph is used to display the solution set of an equation. So that means that when we have graphed a line, that's actually a set of points that are ordered pairs. So it's a set of pairs of x's and y's that make the equation true. So when you have 5x plus 3y equals 8, right? Then 1 for x and 1 for y makes that statement true. 5 times x, 5 times 1 plus 3 times 1 equals 8. So 1 and 1 is true, right? And so then there's lots of other points that also make that same equation true, and the line that we graph is all of those points in one picture. Okay? So a graph is a picture of all the points that make a statement true. And if you remember from things you've done before, we've dealt with inequalities before, right? So if we were to say x equals 5, right? X equals 5. And we wanted to graph that on a number line. We would take a number line, and 5 would be here, and we'd fill it in, right? Okay. But if we wanted to say x is greater than 5, we would use the same number line with a point at 5, or let's say greater than or equal to. So we fill in that dot, and then we shade to the right, right? Because what we're saying is, well, this point 5 makes this statement true. So do all the points to the right of 5 on the number line. So 6, 7, 8, 5.5, 6.2, 7.9, all of those points on the number line make this statement true. All of those x's are greater than or equal to 5. Okay? So we're going to be applying this kind of concept to the two-dimensional space we've been dealing with called the Cartesian plane. So we're going to look at what happens when we have an expression and an inequality, a linear expression and an inequality, and how do we graph it, all right? So for instance, let's say we have 3 minus y, oops, not equals, 3 minus y is less than or equal to negative 5x. Okay? So the first thing I'm going to do is I have to find the edge of this thing. Okay? So just like when you had that inequality, when we had the inequality x greater than or equal to 5, the first thing we do when we have x greater than or equal to 5 is we plot that 5. Because that's the edge of our answer. Here, the edge of our answer is going to be a line. So in order to graph that line, we're first going to solve this inequality for y. Okay? So I'm going to subtract 3 from both sides. That leaves you with negative y is less than or equal to negative 5x minus 3. Now to make the y positive, I'm going to multiply through by -1. Remember with an inequality, if I multiply or divide by a negative, I have to change the direction of the inequality. So I'm going to call this y greater than or equal to 5x plus 3. Okay? So now I have something that's starting to look familiar. All right? To graph the boundary of my solution set, I'm going to pretend this inequality is an equals. Okay? So now this were y equals 5x plus 3. You would say the y-intercept is at 3 and the slope is 5. So let's graph that line. Y-intercept at 1, 2, 3. And then we go up 1, 2, 3, 4, 5 over 1. Okay? And we graph that line. Now, because this is greater than or equal to, we're going to make our line solid. You'll see in our next example, if it's just greater than or less than no equal to, we make this line dashed. Because this line is included in our solution set. All the ordered pairs on the line y equals 5x plus 3 would make this statement true. All the ordered pairs on the line y equals 5x plus 3 would make the statement true. So we include all of them in our solution set. Okay? All right. Now, but we don't only want the ones where y is equal to 5x plus 3. We also want the values where y is greater than 5x plus 3. So if you can see on the camera, my line is right here. Okay? So it has a positive slope. It's sloping this direction. We want to go above it. Okay? So it'd be easier to tell what's above it if our line was something like this, right? It'd be like that. But because it's sloping this way, we know that we want to go above it, which is up over here. This would be below the line, since it has this positive slope, to the left and up. Okay? And you can kind of think through this. If you think, okay, I need 5x plus 3 to be less than y, and so if right here they're equal, and I keep the x the same but make the y bigger, that y is still going to be greater than 5x plus 3. So then what happens is I shade in this whole area. Okay? When you shade on a smaller graph, I want you to do it this way. So let's pretend this was that graph. That line went about like this. Okay? Your shading should be vertical or horizontal lines. So they should go like this. Okay? So your graph, on graph paper, using a straight edge for your boundary line, the line where y is equal to 5x plus 3, use a straight edge for that line. Then you shade using vertical lines above the line because y is greater than above 5x plus 3. Okay? So that's one example. Another example would be we're going to now do an example where it's just less than or greater than. There is no equals. Okay? So let's say that example is 10x plus 8y is less than 64. Okay? So again, the first thing we do is solve the inequality for y so we can graph a boundary line. So minus 10x is 8y is less than negative 10x plus 64. Divide both sides by 8. Y is less than negative 5/4 x plus 8. Okay? Cool. So, we now know that our the boundary line has a y-intercept of 8 and a slope of negative 5/4. But that boundary line now, we don't want to include it because this is just less than. So y is always less than these. The solution set does not include the places where y is equal to negative 5/4 x plus 8. Okay? So we're going to plot out that line, but when I use my straight edge and go along it, I'm not going to fill it all the way in. I'm just going to make it dashed. Okay? Just to show that I'm not including those. It's like when you graph on a number line for an inequality and you do an open circle. It's sort of like an open circle. It's a dashed line. Okay? So we're going to go to 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then I'm going to go down 5, right 4. Down 5, right 4. So 1, 2, 3, 4, 5. 1, 2, 3, 4. That's my slope of negative 5/4. Okay? 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay? And I'm going to make that a dashed line. So just like dash, 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 dash. Okay? And those dashes continue on to infinity. And now, in this case, I want my y to be less than that boundary line. So I would come under this line and shade all of this in here. Okay? So go like this on that side of it. Cool? So that is linear inequalities. That is linear inequalities. When we come together again in class, I'll have some exercises for you where you can write and graph some inequalities. All right? I will see you soon. Happy mathing.